The one thing that can be difficult when we learn statistics for the first time is that there's often a lot of hypothesis testing methodologies that are taught in the course, usually at the end of the course, in the final crunch before taking that final exam. And so sometimes it can be difficult to figure out which test to apply in which particular circumstance. And the first time that you may have to do that may be on that final exam, because typically you learn these tests in a sort of more narrow context. You do an entire section where all you're doing is z-tests, and all you're doing is t-tests, and all you're doing is two-sample t-tests, and all you're doing are chi-squared tests. And so when you are just given a problem and you have to for the first time, figure out, okay, so is this a t-test, or am I supposed to be doing a two sample proportion test, or can I run a chi-squared test on this? What do I do? So sometimes it can be useful to think about what are all the available tests, and how to identify, how to recognize what are the things to look for when you're looking at a problem and you're trying to figure out what test do I use here. Now, I've put together this discussion for about 8 different tests. The typical parametric test that you learn in a traditional introductory statistics course, give or take. But of course, if you're doing a sort of a 2-semester statistics course, you may be looking at non-parametric tests as well. There may be many, many other options, multiple different kinds of ANOVAs, for instance. And so this is not at all a comprehensive list, but typically if you can identify particularly the parametric test that's equivalent, usually the non-parametric versions are similar in terms of what to recognize. It's just, am I doing a parametric one or a non-parametric one? And so this will still be helpful if you are still confronted with non-parametric tests. First, identify the parametric version of the test that you would use, and then from there go on to figure out, should I use the parametric version or the non-parametric version? But in this discussion, we're just going to look at sort of the 8 most common parametric tests, hypothesis tests. All right, so let us first consider the z-test. Hypothesis test for one variable. Now, when you're considering the z-test for means, basically, you have to ask yourself a series of questions. So first of all, is this in fact a one variable test? Is there only in fact one variable? The other thing that you have to ask yourself, is sigma known? If sigma is not known, you should not be doing a z-test, generally speaking. Now, if sigma is not known, then the best default is to go to a t-test, which we will come back to. If the sigma is known and the sample size is very small, you shouldn't be doing a z-test either. But if the sigma is known and the sample size is greater than 30, and there's good reason to think that the distribution is normal, maybe it tells you so in the problem, then the z-test is appropriate. If you're not sure that the distribution is underlyingly normal, you may need larger sample sizes in order to get your test to be more appropriately valid. When in doubt about some of this stuff, go to the t-test. The t-test is designed for dealing with these additional uncertainties. The z-test really is, even though it's the first test that we learn in most statistics books, it is usually just a special case. We used it a lot in statistics when it was harder to look things up, when it was harder to do t-tests numerically, because looking up the t-test values was more difficult, and we use z-tests as approximations. But in modern statistics, we don't have those problems. We don't have to use tables. We just put stuff into, Excel or a statistics software, and it spits out our numbers that we need. So really, you should be using the z-test only, especially if it's not like specifically saying use the z-test for this. You really should only be using it in certain special cases where sigma is known, not from the sample, but from previous work, like it tells you sigma is blah, not we obtain the standard deviation from the sample to be blah, because that's not sigma. And the sample size is big. And again, big is a little bit subjective. It can be smaller if you know that it's normal, but generally bigger is safer. Now, the t-test for means is what you use when those conditions for the z-test aren't all there. So if you have a small sample size, you use the t-test. Again, this is a test for means. So you're looking to see if you have a mean that's given to you in the problem. You have to have both the standard deviation and the mean. If sigma is not known, you use a t-test. If you're given the sigma from the sample, you use a t-test. If the sample size is small, you use a t-test. If the data set is approximately normal because you looked at it, but the problem doesn't say that it's necessarily normal, then even with a larger sample size, you would be better off using the t-test. So when you're doing tests for means, t-tests are really the default. And then z-test you use basically only when like the universe has aligned all the stars in perfect configuration for you. Now, the z-test that you do much more frequently is the z-test for proportions. And so the thing to keep in mind about a z-test for proportions is there is no standard deviation in the problem. So if you're just given a single number, sample size, and one other number, whether it's a percentage or whether it's a count, those are really proportion problems, because proportion problems don't come with standard deviations. But so one of the things that you want to watch out for is whether you are given the count out of a certain total where you have to create your own proportion, or whether they're giving you the proportion. Depending on what kind of technology you're using to calculate this, you may need to convert the proportion into a count in order to do the test. Or if you're doing it by hand, you may need to convert the count to a proportion. Now, in typical introductory statistics courses, it is extremely atypical to have a sample size which is too small to use this z-test with. Technically, there is a test that you should test to see if your sample size is sufficiently large given the proportions you're working with. But one thing to kind of keep in mind is that if the sample size is in fact too small, if it fails that test, you have to use the binomial distribution, which is not something that we typically cover in, again, an introductory statistics course. You may see some examples way back in the binomial chapter before we even talked about hypothesis testing, but that is extremely atypical for problems at the end of a semester. But again, keep in mind that sample sizes are typically quite large, much larger in z-test for proportion problems. So you generally don't have to worry about it, but there is a requirement for approximating the binomial distribution with a proportion, approximating a binomial distribution with the normal distribution that does need to be met. But again, most of the time that is not an issue. The one thing you kind of really have to watch out for is that some problems that give you percentages are not proportion problems. So for instance, alcohol content of wine is measured in percentages. And so they may give you, okay, we did a sample of 100 wines and we found a mean alcohol content of 13% with a standard deviation of 3%. That's a standard deviation problem. That's a means question. That is not a proportion question. So that is the sort of one thing that you kind of have to kind of keep an eye out for. Just because there is a percentage in the problem does not mean that it is a proportion problem. particularly if it's paired with a standard deviation. The test, by the way, that you have to check is typically that NP and NQ are both greater than 10, or NPQ is greater than 5 is somewhat standard as a test. Typically, you want it to be the higher the better, because the better the approximation will be. But you can generally get away with it, and most problems in introductory statistics courses will meet this definition without any difficulty. Now, let's think about two sample tests. If you have two samples, again, two sample tests for means can be a little bit complicated. Sorry about the phone ringing. Can be a little bit complicated because you have to first determine if the tests are independent or dependent. And then if they're independent, there's two different ways that you can go in terms of the mechanics of the calculations. But let's look at the dependent case first. Now, the thing about the dependent case is that you have to have the original data. And the reason that I say that is because you have to calculate the differences for each pair of data. Now, dependent data will typically not only give you the raw data because it has to, but it will also talk about terms in the problem that indicate that it's paired or it's dependent. So it will use things like the term pair, or it will use things like matched. It could be a before and after scenario where you take one person, you give them a test, you train them after you get the test score, and then you have them take the test again to see if there was an improvement. Or you may see a scenario in the problem where they say specifically, we had X number of students and they were split up into two evenly sized groups, and then they were matched based on their IQ or their socioeconomic background or something like that. They're trying to construct a paired test when they say things like that. If the data is displayed in pairs, so two columns of data, pair one, pair two, or they're measured under similar circumstances, different baits in the same lake at the same time, for instance. So think about those kinds of features in the problem. Again, look for those keywords like paired or matched. Another thing to kind of think about is, are the two sample sizes the same? If the two sample sizes are not the same, this is definitely not a paired test. And so you should try the independent test. Now, having the sample size the same is not a guarantee that it's paired, but if the sample sizes are not the same, then you can reject this idea and go on to some other option. And again, typically t-test is the default. In theory, you could have z-tests and things like that for these kinds of structures. But again, as we noted in the one sample case, z-tests are really like special cases that almost never apply. And so we just stopped talking about z-tests for means when we get to the two sample case typically. Now, this test basically the two sample dependent test. It basically, because you're taking the differences of each pair, it basically turns your test into a one sample test. So in terms of the calculation side of it, but you do have to have the raw data in order to make those difference calculations. So no raw data, it's not paired. Now, for the independent case, there are, again, there's kind of two versions of the independent case, and the reasons for using them are basically the same, except for a difference in assumptions that you're making when you conduct the tests, which changes the way that you calculate them. But the first thing that you want to do is you want to identify, are they independent? So if you have two samples, if the two samples do not have the same number of samples in each group, it's independent. It's one of these. Because it can't be paired. If they are different, if they're the same size, they could still be paired. They still could be independent if nothing in the problem is describing them as being matched or paired. But you do have to distinguish this very carefully, because you will get different results if you're supposed to do it paired, and in fact it's not. You calculate it as unpaired. You need to, again, check the data to see that it's not dependent. How was the data collected? Was it just like random men and random women with no effort at matching them, for instance? Again, look for those key words to distinguish dependency by they were matched for particular criteria. If it's, again, not a before and after case or things like that. But again, this is very common. Now, the main difference between the pooled versus the unpooled, so the independent case, typically I think of as the unpooled case. In the pooled case, all the conditions are basically the same, except that in the pooled two-sample t-test, you're making an assumption that the variances or the standard deviations for your two samples are the same or similar. Now, in sophisticated statistical analysis, you could do a test on the standard deviations, on the variances, to see if they are in fact close enough. Often in an introductory statistics class, we don't do that step. We just kind of eyeball it, or we make the assumption, whether it's justified or not. But technically, that is the condition for the pooled case. Again, it's fallen a little bit out of favor. It used to be a little bit easier to calculate, and so these assumptions were typically made. But it typically, in sort of the modern statistical regime, the unpooled scenario is typically sort of the default, because you don't need to make that assumption. They might be the same, they might not be the same, but we don't really care because we're not making that claim. In the pooled case, you are kind of making that claim. And so it's typically better, if you're not sure, to use the unpooled than the pooled case. But if you are going to use the pooled case, then you should at least check to see that the variances are at least approximately equal. Now, again, there is a two-sample z-test, but it's almost never used. A lot of the, for means, a lot of the assumptions that we noted were made previously have to do with whether the standard deviation of the populations are known, things like that. Again, it almost never pans out in the real world. And so it's one of those things that you can kind of, yes, there conceivably is a way to do it, but it's not really on the menu in any practical way. Now, the z-test that you can conceivably do is for the two proportion z-test. So we had the one proportion z-test, two proportion z-test as well. Again, the main difference between the one sample proportion and the two sample proportion is that there's two proportions. Again, they can come in probability, they can come in percentages typically, or counts. Just because the problem has a percentage, same caveat as before, does not necessarily mean that it is a proportion problem. So it could be a mean problem, like mean alcohol content, for instance. So you want to double check and make sure like it's a percentage, but there's also no standard deviation listed in the problem. Now, if you have three or more proportions, you typically go on and you do a chi-squared test or some other kind of test. This is two proportion test is like the special case for when you have exactly two proportions. Often these problems can be given in the form of a table that is similar to a chi-squared test. But you do want to also double check your sample sizes. Again, this test is not designed to be very, very small sample sizes. There are other tests that you can use if in fact your sample sizes are very small. again, not typically covered in a introductory statistics course, but there are non-parametric versions and things like that that you could do, as well as simulations and permutation tests and bootstrapping and so on. Now, the one-way ANOVA essentially is the three or more means version of a two-sample pooled test. If you have only two samples, in theory, you can get away with using an ANOVA, but it's typically not done. Textbooks really, and as an instructor, I frown on it, even though you do get the same results as the pooled case. And my guess is that this is probably why pooled was somewhat more common in the past. But the one-way ANOVA is designed for three or more categories, three or more samples that you're trying to compare the means of. Again, it's not appropriate really to use it with two samples. But it is equivalent to the pooled case because the ANOVA is assuming that all the variances are at least approximately equal. This is one of the reasons why it's not, even though it technically is somewhat equivalent to a two-sample case, the unpooled is preferred rather than the pooled in the two-sample case. There's no restriction on data set size here. Textbook problems typically have small data sets. A lot of textbook examples have equal size samples for each of the categories. That is not required. But the test for the one-way ANOVA is basically taking all of your means and saying, are all of them equal to each other or is one of them different? If you reject the null, then you can do pairwise t-tests, or you can do Tukey's method in order to determine how they group together. But if the null is not rejected, we're saying all the means are equal, and so there are no meaningful differences between them. But three or more samples, three or more means problems. Now, we can also do tests on correlation or slope in a regression context. This is hard to mess up with the other tests because, again, you have to have the scatter plot. You have to have, typically in most of these problems, you have to have the raw data. If this kind of test is going to be confused with another kind of test, it's typically the dependent two-sample t-test case, because I have seen students calculate correlations on those as if they were a scatter plot type regression problem and not just a two-sample dependent question. So that's the main thing that you should worry about. These are, again, always done with t-tests. A lot of, especially textbook problems, don't have terribly large sample sizes. And we, by definition, don't know what the standard deviation of the population is. Now, there are tests that come with regression tests. The model utility test is essentially an ANOVA test, testing whether your coefficients in your regression model are 0 or not. And so in that sense, it has a similarity to ANOVAs, and sometimes the model output will output the data, output this model utility test and describe it as an ANOVA test. Again, typically this is just testing whether all the slope coefficients are 0 or not. This is not really a lot different from the sort of one sample test unless you're doing multiple variables in your problem. This will just, the regression model utility test and the slope correlation test will be identical. Now, goodness of fit tests, these tend to come up in contexts where you have one set of data that you want to fit to a distribution. Like the chi-squared test that you use the chi-squared distribution for this as well. Instead of having a two-way table, you have basically just a one-way table with outcomes and then the counts. You have to calculate the expected outcomes in order to do the test. And that's really the hardest part of the goodness of fit tests. The results of your test will not be meaningful if you don't use the correct distribution to calculate the expected counts. But basically, you have to calculate the probabilities of each of your outcomes, your siloed bins typically, and then multiply by the number of observations in your sample in order to get the expected counts. But again, the goodness of fit tests you use when there's basically just one row of data. There's one row of observations. The difference between that and the test of independence or the setup for the test of homogeneity, those are typically two-way tables. So again, 3 or more outcomes in at least one direction. Otherwise, it's a test of two proportions, basically. And you have to have, again, at least two rows of outcomes. So it's a table rather than just a row of outcomes. Now, the test of independence and the test of homogeneity are very similar. The main difference is how you calculate the expectations. In the test of homogeneity, you basically take your total outcomes and you divide them up evenly across all of the outcomes, and then that's what you test the expectations against. In the test of independence, you're using basically this conditional probability rule. You're making the assumption that all of the outcomes in the table are essentially the product of outcome A times outcome B totals, and then converting those to, again, counts. And that's the assumption that you're making. Once you have the expected counts, everything else about these two tests is completely the same. It's just that tricky step is the difference in calculating the expected outcomes that makes the difference between these two tests. So, and then of course the test statistic and probabilities are calculated with the chi-squared distribution in both of these cases. And again, there's not at all, these are not at all the possible outcomes. The possible tests, I mean, there's two-way ANOVAs and there's, as I said, non-parametric tests and things like that, depending on what else you are looking for. What else is covered in your course, but these are the sort of typical outcomes. Now, one thing to think about as you go through problems is ask yourself these questions. Does the outcome look like what I was expecting or doesn't it? So just as a typical example, let's look at an example and see if we can identify what it is. So we have this table of observations. It looks like just a list of single values. From raw data, they're numerical. We can calculate means and standard deviations. There doesn't seem to be any discussion there doesn't seem to be any discussion of separating it or anything like that. We have a previous mean is suggested to be 55 kilovolts. So this is a one sample test. The sample size here is large enough, but the problem doesn't say anything about whether or not it's normally distributed. So my thought is it doesn't say it's normally distributed. It doesn't give us a prior sigma. We should conduct a t-test, even if the sample size is bigger than 30 or 40. This is a Pew Forum survey. 25% that said they believe in astrology. This is a proportion question. Previous surveys said 23%, again, we want to see if it's similar. Does this represent a significant increase from previous years? So we have our percentage. It is in fact a proportion of the total. And we want to calculate the samples, the hypothesis test. The one thing that we are missing in this problem, oh no, here it is, 2003 results. We do have the sample size and the proportion. That's a one sample proportion test. So those are the kinds of things that you're looking for when you're looking for a problem. So here's an example of a two sample test that could possibly be paired. Notice everything is counted, 1, 2, 3, 4, 5, 6. We have indoor versus outdoor. For a sample of houses selected from a certain region, determine if the indoor and outdoor measurements are different. So this is a two sample test. You can see that the pairs are numbered with each other. Therefore, a similar region, indoor and outdoor levels. This would be a dependent, two sample dependent t-test. So again, these are the kinds of things that you're looking for as you go through these problems. The whole point is, again, you want to be able to identify what kind of test you are conducting. So if you go through these questions and you kind of ask yourself every time you see a new question, how much information am I given? Does it look like it's broken up into two groups or one group, or there are no groupings, in which case it's one group? Are there 3 or 4 groups? Is this do I have a percentage or a count? Do I have a mean and a standard deviation? Can I calculate the standard deviation from the data, or is it stated in the problem? And those are the kinds of things that you're looking for in order to determine what kind of test are you looking at. And then you can follow the procedures for how to calculate those tests. But sometimes the trickiest part is identifying the correct test. I've noticed that my students have a particularly difficult time distinguishing the two sample t-tests. Is it dependent or independent? That's sort of the big hang up. But there are other places where you can get these things confused, and you can't really force a problem into a scenario where it doesn't actually fit. So if you're trying to force a proportion problem into a means test, you don't have a standard deviation. You can't just sort of make one up. So identifying that test that you have to use is sort of that key crucial first step.